All right, I think that I will get started here. So this session will be devoted to an introduction to machine learning. Um, the hope is the kind of approach to teaching machine learning that I take is to show you bits of code and show you very little math. Although it is a heavily mathematical field, there's a way to gain intuition about machine learning that I think also kind of serves you as you're going forward in NeuroHackademy and maybe also in neuroimaging work that's based more on thinking about the intuitions, the bigger picture intuitions of what machine learning is for and what kinds of problems it's trying to solve. And then looking a little bit at code, both as it works with actual data and then with some simulated data to gain a little bit of an intuition about the main concepts behind that machine learning kind of works around. So that's the purpose of this session, how it's designed. We'll dive right in. There is in the curriculum folder on in your hub in the curriculum folder, there is a Rokem-ML folder. Did I make a Slack channel? I should make a Slack channel if I have not yet. I have not. Let me make a Slack channel for us as well. Oops, channels, add.
Sorry for interrupting. We cannot see the screen
Oh, I
yet.
need to share my
Sorry.
screen, of course. Thank
Thank you so
you.
much.
No, that's
You're
my
welcome.
bad. All right. Okay, sharing my screen
Great.
now,
Thank
and
you.
we can use this Slack channel, Rokem-ML. And okay, so there's a series of notebooks here. There's 6 notebooks. I'm not sure that we will get through all of these notebooks. The first one is really more of a preliminaries and data, and we really don't need to spend much time about it. One of the data sets that we will, so this is more for people who are using these notebooks for self-study and maybe useful for folks maybe watching this after the fact. And it just emphasizes that the notebooks, you can run those notebooks as I'm kind of walking through the notebooks, and you can make little experiments in them. There's a little bit of an explanation about kind of how to install this when you're not working in the hub. And then there's a little bit of an introduction to a data set that we'll use. We'll get, maybe I'll introduce that later when I come to that data set, which has some brain data from this paper that we use. But that's the preliminary. So 1 of 6 down, we're on to the next one. I promise to be a little slower on the next one, and just in general. Okay. So as I said, we're going to do a walkthrough of these notebooks. I won't read every word that's written in the text because the notes are supposed to be also for someone who kind of reads this after fact, for you as you're reviewing this. But I will kind of pause on pieces of code. So I'm hoping that throughout this day and now as well, you've already started seeing how we work with Jupyter Notebooks, or maybe you're familiar with Jupyter Notebooks. Here we're going to use a series of libraries. We sort of explain how we use these libraries. As we'll use each one of these, I'll explain more. So start by importing, that's kind of at the top. And then to sort of a bit of definition. So, if you're new to machine learning, you might be wondering, what is this thing, machine learning? You might have heard that it's used in all kinds of ways to do interesting things. And then you might be wondering, so, okay, what does it encompass? We think of machine learning as the field of science and engineering that builds systems that are capable of learning from experience, learning from data. So all of the kinds of systems that you'll see here today are systems that observe some data and learn something from it so that they can make inferences about subsequent observations, or they can infer some parameters about the world. They create some model of some section of the world. And all that is done by the observation of data. So You can think of an alternative, which is a system that learns by explicit instruction, right? You tell it, when you see this, do that, or when you see this other thing, do this. This is not the case here. Instead, machine learning algorithms broadly, or machine learning systems, are systems that observe data and change in accordance with that data in order to either infer some parameters or make inferences about subsequent data. And this is a very broad definition. We'll go, of course, in a lot more detail here into examples. One important thing to put up front is that this is quite different. The goals of machine learning are quite different than the goals of, say, standard statistical methods, in that we will make our objective an accurate description or accurate prediction of the data, rather than a concise interpretation, a concise parametric interpretation, or the ability to make kind of parametric inferences with accurate, let's say, statistical p-values associated with that. Our goal will be to seek the accuracy in representing the data and in predicting. And so the goal of many of these kinds of systems is to make accurate predictions on held out data, or on data not observed in the training. We'll talk about why data needs to be not from the training data, but that's sort of a general attitude. And there's a lot to read about this. There are nice papers from the statistics literature and from the kind of machine learning literature that describe these distinctions. One in particular that I'll recommend is a paper that Tali Arconi and Jake Westphal wrote in 2017 that explains machine learning in the context of psychology and psychology research, and why machine learning thinking needs to go into statistics. So setting aside this kind of theoretical distinction, let's go into a little bit of breaking apart this idea of machine learning, and maybe we'll kind of learn more about what machine learning is by looking at a few examples. So machine learning, we broadly distinguish between different kinds of tasks that machine learning models or algorithms do. One broad distinction is between what we call supervised and unsupervised learning. In supervised learning, we observe features of the data, and we might observe what we call labels of the data. So there are a few examples here. For example, one that's quite popular in the neuroimaging literature would be the prediction of people's chronological age from structural brain features. So in this case, the label associated with every observation is their age, and the features, what we call the features, is maybe a series of measurements from different parts of their brain, recording something about the brain structure in those parts. Another kind of supervised learning situation is determining whether or not incoming email is spam. So in this case, the label is spam or not spam, and the features might be the collection of words that are in that email. Or maybe another option is, out of a collection of words, which ones appear in this email. You can think of both of those being input features. And then other supervised learning, and other supervised learning tasks could be predicting a person's rating of a particular movie based on their ratings of other movies, diagnosing schizophrenia based on genetic markers. All of those have sort of a label associated. In this case, the rating of the target movie based on the other ratings, or in this case, schizophrenia, not schizophrenia. And in all these cases, we can kind of arrange to have training data that contains both the labels and the features to show the system and teach the system, and through observation of this data, how to perform these different tasks. In each of these cases, we assume that in this training data, we have a ground truth. That is, we have labeled examples of spam, of movie ratings, of schizophrenia diagnosis, in addition to many different features. within the broader kind of framework of supervised learning, we also make a further distinction between classification tasks and regression tasks. And the way this is built, this kind of lesson plan is built, is to start maybe from one that's potentially the most familiar, but also the one that's easiest to explain, which is regression. So regression problem is a problem in which set of continuous numerical labels. We have a set of continuous numerical labels like age of the individuals. Those are the labels that we're trying to predict. And we're using one or more features to try and predict those labels. So here's an example of relationship that can be conceptualized as okay, I'll do this. Can you see the code when I do this kind of thing? Sort of. Okay, let's try that. So here what I've done is we fixed the seed to produce deterministic results, and we'll do that in many places here so we know what we're doing. Generating X values that are taken from a random normal distribution, 30 points, and then I am generating labels Y that are generated from a systematic relationship, in this case, X times 0.5, and adding some noise to that. So this is a very simple linear relationship. In this case, the regression problem, the machine learning problem, has one label, the Y, and one feature, the X. And in the simplest case, we can fit what's called ordinary least squares regression. Here is the ordinary least squares regression written out quite explicitly. We create what we call sometimes a design matrix, which is a matrix that has the input features and another column of ones, which will account for the offset or intercept. And then we solve it with this inside of the NumPy library, inside the linear algebra sublibrary, there is a least square solver. It takes this kind of matrix X with the additional column of an integer of the ones for the offset, and it takes Y, and it solves that, and it gives you parameter estimates for the intercept, in this case negative 0.36, and for the slope. And you can see that, you know, in the original way that the data was generated, the slope should have been something like 0.5. We added some noise, so that messed that up a little bit, and there is no intercept. So these are estimates, and you can see the best fit line through this thing. And so this is our model, and it gives us a prediction that we can write out as y hat equals negative 0.37 plus 0.62x. So if I gave you a new observation, a new x, and asked you what do you think y should be, you can plug it into this equation and give me a y hat that we can then evaluate against the true y. So this is a very simple case of regression, and we'll see as we keep going, we'll see a lot more complicated cases of regression. For example, you might imagine that instead of fitting this kind of straight line, we might fit something else here, or maybe we'll have a lot more features and we'll need to deal with that. But for now, this is the way that we think about regression, and it's very similar to the ways that you might have seen linear regression presented in statistics classes. But instead of telling you, okay, now let's estimate, I don't know, the p-value associated with this parameter, I'm telling you, okay, what if I gave you some new data? So it's the same math, it's just a little bit of a different attitude attached to it. Okay, another kind of problem are classification problems. Those are also supervised learning. Here's an example of a setting for a classification problem. We'll come back to scikit-learn. Scikit-learn is a great library for machine learning, and really this entire tutorial, part of its goal is to introduce you to scikit-learn. Out of curiosity, who here has used scikit-learn? Well, there's a couple of you. So we'll introduce all of you to scikit-learn later on, and one of its benefits is of the scikit-learn is A, it's got a lot of nice features. B, it's got an application programming interface that helps you think about machine learning in a way that you'll see in a little bit. But for now, what we're seeing here is how we use it to generate examples. So it has some code to generate examples. We're using this make blobs function that makes, as its name suggests, two blobs of data. You can determine how many centers you want or how many different classes. And depending on how you set this exactly, those can be more or less distinguishable. So in this case, now we have a label that is a binary, yellow or blue. That's what's going to be in this Y. And we have two features. The X, what we call X, which is our feature matrix, has in this case, how many, I'm not sure how many we made here, so let me add some code here to y.shape. Yeah, there's 100 points here. So y is 100, in fact, I'll just show you why. It's 100 numbers, 0 or 1, which is the binary classification. Are we blue or are we yellow, one class or the other? You might think maybe, I don't know, cats and dogs or something like that, two different classes. And then the X matrix, in this case, the matrix of features, has 100 rows and 2 columns. And the 2 columns correspond to the first axis and the second axis in this. So every point here is defined by a set of coordinates on this 2-dimensional space and a label that's a binary. And so in this case, our task is to receive 2-dimensional coordinate, the X, and say, is this yellow or this is blue? In this case, this task might not be too hard because all the yellows are in one corner, all the blues are in another corner. But maybe, let's see, here it might be a little bit harder. They're a little bit more intermixed. And so this we call a linearly separable case where we could draw a straight line here. And if it's on one side of the line, then we say it's one thing. On the other side of the line, it's another thing. This might not be as neatly linearly separable. You might imagine other settings where, I don't know, there's yellow on the outside and blue in the middle, which is also not linearly separable. And as mentioned here, there could be a situation, many real world situations, classes may be intermixed in a way that you're not going to be able to do a 100% accurate classification. Okay. Yeah, here's here's a 5-class classification problem with things intermixed, much harder. Okay. So those were 2 kinds of supervised learning. The next thing that I'll mention here is also that there is a whole set of problems called unsupervised learning, and those roughly split into 2 kinds of things. The first is clustering, and the other is dimensionality reduction, where we had labels and features, y and x in the previous problem. Here, instead, we have only x and not labels associated with x. We might imagine that there's a latent set of labels associated with the data. For example, if we get data that looks like this, we might say, well, this looks like it's actually 3. There are 3 underlying classes. But the training data that we receive, the measurement that we receive, doesn't come necessarily with a y that tells us what each one of these is. And in clustering, our goal is to derive out a good set of good grouping of this, or good labels that we could associate with that. Sort of to discover from the data what are the clusters. So you know, in this case, maybe we'll cluster this way. Again, you might have a situation where the truth is something like that, the thing on the left, but what you see is this thing on the right, and it's very, very hard to cluster it in any meaningful way. So those problems can also be pretty hard. The other kind of class of problems in unsupervised learning are what called dimensionality reduction. Here's one way to think about dimensionality reduction. Here again is a set of data. It's marked as X and Y, but you can think of this as data that's unlabeled, you have two features. So you have each point here is defined by two coordinates or two dimensions. But if you look at this data, you might say, well, we have a description of every point that requires less than two dimensions. We might come up with a description of each data point that requires less than two dimensions. The description we've been given is an x coordinate and a y coordinate, but let's, for example, imagine that we, instead of describing each data point as an x coordinate and a y coordinate, we describe each data point as a distance from the lower left corner along this line. Now that's a one number instead of two numbers, and we haven't lost a lot of information because all of these data points sit roughly along one line. And so we lose some of the information about their scatter in this direction, but most of the variance in this data is captured really by one dimension, which is the dimension that goes diagonal. And that's the spirit of dimensionality reduction problems. Generally, we might come back to dimensionality reduction much, much later if we have time. Okay, what questions do you have so far about kind of just this topology of machine learning? Yes. Yeah, that design matrix, the thing that I kind of distinguished it by is that I added a column of ones to it to capture the additional kind of offset. So you can think of if in addition to capturing a linear relationship, we also want to give it like the offset to kind of capture the offset, then we add another one and maybe I call it a design, but it's not, that terminology is not super, I wouldn't, the much more important for our purposes, this set of features X. And you'll see later, some of the algorithms, we simply tell the algorithm, fit this with an intercept as well. And then under the hood, it does what it needs to do in order to capture them. Okay, what other questions do people have? All right, let's look at some data. So throughout this tutorial, we're gonna use this data set. It's the ABIDE2 data set. ABIDE is the Autism Brain Image Data Exchange. It's sort of one of the early attempts to aggregate data from many different sites, structural data, structural scans that were aggregated over, I don't remember exactly how many sites, but many, something on the order of 20 sites. In each site, they collected data from individuals with autism and healthy controls. And the data that we're looking at here contains the name of the site, some subject identifier, their age resid that we'll come back to later, sex, and whether or not this individual is diagnosed with autism, and then a bunch of features extracted using FreeSurfer. So we have the area of various cortical regions, their thickness, and other things about them. So the data itself has 1,004 rows, which are 1,004 subjects that were collected in this data set. And then there are 1,446 columns to this data frame that I showed you here that we read from a TSV file that's stored on the hub. And the first six columns here, group, sex, age, age, subject, site, are sort of, you can think of these as like phenotypical label kinds of information. And then the other 1,440 are all features. That's going to be our X. So we'll use this data as an example for kind of high dimensional data. One of the things machine learning is for, and we'll see throughout this tutorial, is for dealing with data with very, very high dimensionality. In particular, this data has more columns than rows, which poses all kinds of interesting statistical problems. Like I said, we're going to use scikit-learn. It's a really great machine learning library written in Python. One of its features that make it so, the design of the software is great. It includes many different algorithms, but one of its real highlights is its stellar documentation. You can read this documentation a little bit like a textbook in machine learning, applied machine learning. Tons of worked out examples on interesting different data sets and very detailed explanations with references to the relevant literature. It's really, really great. data and scikit-learners are presented sort of in the way that I've been talking about so far. It uses the NumPy array as its main kind of data structure. You would have X arrays that contain the features, in this case, 1,004 rows by 1,440 columns for the data. So here's our feature set. X all in this case is all the columns and all the subjects. We've used the filter function in pandas to filter and select only the columns that have FS. FS is for free surfers, all the features. And here it is. It's, in this case, we're looking just at the head, 5 rows and 1,440 columns. It's just the part of the original table that has the free surfer features. And then we might, in this case, for a label Y, select the age, the values. So the way we select the column age, and then values turns this into a NumPy array. So we have a column NumPy array that has all the, or one-dimensional NumPy array that has all the ages. We're going to start with the regression example, sort of mirroring the example you saw before, but now in many, many dimensions. The API, the application programming interface of scikit-learn, has this kind of uniform flavor to it that you'll see soon. The library implements a series of what are called estimators. Estimators are classes or objects in Python that know how to estimate some model. So one example of that is, okay, we'll start by doing some selection, and then I'll show you one example of this thing. So here we're selecting 5 features. So we're sampling 5 columns from our 1440, and we have our Y is the age. So the data we're going to use in this case is x.shape, y.shape, just to give you a sense, is 1,000 by 4 by 5 randomly sampled columns, just for conciseness here. And the age is 1,004 age values for these subjects. And here we're going to instantiate the linear regression. So inside of the scikit-learn library, there's a submodule for linear models. And in the linear models, there's linear regression. It's very similar to the linear regression that you saw just before, but the numerical details are hidden under the hood. The way that scikit-learn estimators operate is that we start by initializing the estimator. So we have our class here, or our kind of class definition, and we instantiate it, in this case, instantiated with an empty set of parentheses. And that's because we're using the default values of instantiation. We can give it some parameters that set it. For example, it has a fit intercept equals true. Oops. Well, that's not what I want to do here. Fit intercept equals false. If we instantiate it like this, then it now would not fit the intercept. So this is about whether or not to add that column of ones. But in fact, we do want to fit the intercept. So we're going to keep that true. So our object has a fit intercept attribute that's set to true because that's how we instantiated it. Notice that this linear regression model hasn't seen any data yet. So initially, at least, it has no estimate of parameters. It hasn't learned anything yet. And that's the next thing that we do. And all of the estimators in scikit-learn, there's what's called a fit method. Method is a function of the class. So in this case, a fit method that takes x and y, and when we pass x and y in, the model is fit, and now we have a model that has been fit, and now it has an estimate of the intercept, 53.81 in this case, 53.81 years, right? That's the estimate for the, and then some parameters or coefficients that are associated with each one of the 5 columns of the matrix that we gave it. So it says, okay, this first parameter is pretty important. The larger that parameter is, the younger we think that person is. This one's not so important. This one's even more important. The larger it is, the younger the person is that we think. And these two are not so important either. They vary dramatically in size. And the reasons are rather prosaic in this case. We have parameters with different, the features have different units, so some of them have a lot more effect than others. But we're kind of abusing the data a little bit here. What we have gotten from this is an equation. It's very similar to the equation that you saw before. So you remember the linear regression equation you saw before. In that case, it was y hat equals 0.6x. Here we have instead y hat equals some intercept plus or negative 3.94x1 plus 0.02x2 minus 8.92x3 minus 0.01x5. So it's kind of like you could think of a line or surface in 5 dimensions plus an intercept that for every set of 5 coordinates that I give you, you'll say, oh, let me put it on this surface, and I'll kind of predict for you the y that's associated with the age. And indeed, you can do exactly that. You can take a set of measurements, in this case, the measurements that we put into the model when we fit it, and you can apply the predict function or predict method to predict some outcomes. So in this case, these are the ages that we are predicting. So we do this operation, we fit, and then we predict, and now we can ask, is this model a good model? Say by plotting, in this case, on the y-axis, the true age, on the x-axis, the prediction. And you can look at that and say, okay, is this good? Is this bad? Ideas, it's a little ad hoc. There's some signal in the data, maybe, that's captured by this model. But, one thing to notice is the true ages go from 10 to 60. The predicted ages go from negative something to like 30, so it's off by something. And there's some nonlinear things going on here as well. But the nice thing is, with just a few lines of code, maybe we have another copy of these lines of code down here. Yeah, here it is. Linear regression, instantiating model, fitting it, and predicting. We can go from data to prediction of that data with a model, and then we can go and do something with those predictions. And I won't go into this, but it's usually not about estimating the parameters and kind of assessing those parameters. Instead, what machine learning wants to do is usually assess the goodness of fit and find ways to improve this goodness of fit. So we use, it's called the coefficient of determination, in order to determine the goodness of the fit in this case. So we're comparing y to y pred, the original labels, to the labels from the prediction from the model, to create what's called an R2 score. And this R2 score, or coefficient of determination, you could think of it as the proportion of variance that's explained by these predictions in the original data. Not to be confused with the Pearson correlation coefficient. This is not that. The math is slightly different, although both of them can be interpreted as a proportion of variance explained. And you can look, there are other metrics you can use here, like this sklearn metrics has, I don't know, mean squared error, I think. Yeah, it has mean squared error, mean absolute error. You can think of other metrics. R2, the coefficient of determination is nice because it has this kind of uniform scale, regardless of the original scale of the measurement. It gives you a proportion of variance, so you can kind of look at it and get a feel, even if you don't know, like, if we had mean squared error, it would be in years, and that's like, is 3 years a lot? Is it a little? We don't know. It depends a little bit on the noise in the day. Depends on all kinds of things. This is a little bit, kind of gives us an intuition at least. So just to go one more step here, if you fit a model, you can actually go directly to score it, which is, it skips a step here. It does the prediction, and then it also calculates for that prediction the coefficient of determination in this case. So every estimator, in this case linear regression, has a scoring function associated with this. For linear regression, it happens to be the coefficient of determination. So when we call on a linear regression model, we call score with x and y, it'll give us the score for that using the parameters that were fit over here. Okay. I'm actually going to skip this autism classification example, there's sort of a different set of, when you're doing classification, there's a different set of metrics that you can use for goodness of fit. It gets a little bit complicated how you do that. So that's down here as well. Yes. You have a question? Which? Oh, that depends a little bit on your question, right? If your question is something like, how does the brain age or develop? Then you might want to ask a more like a regression question. If you're interested in what is there information about differences between people with autism, people without autism in brain measurements, you might be asking more of a classification problem. Yeah, I mean, a lot of questions that look like classification questions could be reformulated as regression questions. For example, for the autism question, there might be, well, it is a spectrum disorder, right? So there might be a continuum of scores that where some individuals with autism are a lot closer looking to individuals that are not diagnosed with autism. So that boundary is actually in some sense an artificial one. So it's I think good to think, and there's actually like a link here to paper about discretizing continuous data and why that's a bad idea. So I encourage you to look at that. So whenever you think you have a continuous thing, you should be looking at it as continuous. The one thing, without going into too much details, that I will show you here is that if you take, instead of Y data age, you take Y data group, which is a binary. It's got either the value 1 or 2 for autism, no autism. And you use, instead of using a linear regression, you take from this escalator naive Bayes something called a Gaussian naive Bayes classifier, and you initialize that instead of initializing the linear regression. The rest looks very similar. You have a fit method where you give it an X matrix with the features and a Y that has the labels, and you can run a scoring that gives you some goodness of fit scoring on that. So those things are very similar. There's more details here, but I am going to not do that, and I'm going to not do this clustering example also because, but I'll leave the clustering example as an exercise for the reader for later. Just again emphasizing that the mechanics are very, very similar. So for all of these different estimators and different tasks, the API, the software API looks very, very similar. So once you learn how to use one of these, you kind of learned how to use all of them. Okay. So cool. Okay. In the span of a few things here, we could have developed 3 different machine learning algorithms. We'll focus very much on regression here, which is the reason also I skipped over classification and clustering here, but go back and look at those. But it feels a little, there seems to be something weird about this. I'll actually show you an experiment that you can do here that will give you a sense for the fact that there's something strange going on. And that's what we're going to do here is, you remember previously when we fit the model, we selected 5 features randomly. So here I'm doing an experiment where I'm selecting 5, 10, 20, 50, 100, and so on until I use all the features. And I do exactly what I did before. I initialize a model, and I actually run here 10 times the model. So I sample a random set. In every iteration through this experiment, I randomly sample 5 features or 10 features and so on. I fit the model, and then I score the model, and then I store that. And after running that, I can plot a plot of the performance, the explained variance in age, as a function of the number of brain features used. There's an error bar here even across these 10 experiments that I plotted. So this is great. I think we can go home, right? We're basically performing perfectly once we have 1,000 features, and that's a perfect model. So we've kind of solved the brain here, and we can all become astronomers or geoscientists or go solve a real problem. But more seriously, what is the issue with the way this was done? Like, what's the problem with this zero error model here? Yes, please.
Parameters and things that you can kind of predict a different set of data. It's not.
Yeah, the problem, one way to say this, so the what was said here is that it's kind of capturing noise. So you're not going to be able to use this model in any meaningful way. And we'll see we'll kind of break that down later. And another way to say that is that we had 1,004 samples and we had 1,440 features. And if you have 1,440 dimensions, you can, in 1,440 dimensions, you can contrive a surface that passes through every one of those 1,004 points. That's exactly what happened here. In fact, we contrived a surface that simply passes through every one of these points. I'll show you that in a little bit fewer dimensions in just a bit here. But that really is what's happening here. And it's contrived, and we'll see why it's contrived in kind of the next notebook here. I mean, just thinking about it, we can't have a zero error model. There's noise in the measurements. There are even might be noise in the labels. So a zero error model should really raise a red flag for us. And in this next notebook, notebook number 3, we'll see exactly what's going on here, which is called overfitting. So we'll talk a little bit about overfitting and underfitting. So okay, as we saw just now, if we have enough features, we can fit a model that has zero error, and that raises a bit of a suspicion. So what's going on? Let's look at a slightly more and what is actually happening is called overfitting. It's a little bit of a version of what was said here. This is a thing that we call overfitting. And I'll give you another way to look at this phenomenon of overfitting. We're going to look at a slightly different kind of data. So this is data, so we're making some data here. This is data that has one feature and one label. But the label is actually a nonlinear function of the feature. So looks something like this, right? The horizontal axis here are the features. The y-axis here is the label, and what you can see is there's some relationship here between the input, the feature, and the label, but it's not a linear one. And so if we try to fit a linear model here, we're using the estimator, the linear regression estimator, and we're doing some additional indexing in order to get that to work. We get a model that's pretty bad. And that's called underfitting. So we have a model, it has, how many parameters does this model have, by the way, just out of curiosity to see what y'all think? That was answered right there, yeah. There are 2 parameters, one for the intercept and one for the slope. So we have one feature that goes in, but actually 2 parameters are fit to this data to capture the intercept as well as the slope. And if we had said fit intercept equal false, like this, well, that would be even worse because we need one parameter to capture. So this is a 1 parameter model that does even worse. Okay. So one way to sort of deal with this is to come up with some other models, and we'll look at model selection later to sort of think about this more rationally. But one way to think about it is, okay, well, let's create a series of models and see which model works well for this. And one kind of model that we can do is called polynomial regression. Russ talked about it this morning, so you saw sort of an introduction to this. In scikit-learn, you can create a polynomial regression model by using these polynomial features. There's some additional niceness here about using a pipeline API. Scikit-learn allows you to chain together operations. So you can create an estimator out of a series of operations. In this case, the series of operations is you take your input data, your x, you create polynomial features from that, And those polynomial features have some degree. You can choose what degree you want to use, whether or not to include bias. And then the second step here is linear regression. So when we run this make pipeline function, it creates for us an estimator that includes, as a first step, the creation of polynomial features up to some degree. Polynomial features are x, x squared, x to the third, x to the fourth, and so on. So in here, degree 10, we make a pipeline with the first step being a polynomial, a set of polynomial features up to degree 10. And then the second step, a linear regression, and we can fit that in the same way that we fit the linear regression, we're fitting that to an x and a y, and we can predict just like we predicted before. And whoops, I should run this before I run that. And you can see if we have degree 10, this is an excellent model. It captures every wiggle in this data, even this data point up here, it kind of stretched itself down and then up just to reach that one data point and has very small error. Okay. So this is a little bit similar to the problem of, you remember I told you if you have 1440 dimensions, you can contrive a surface that passes through every one of your data points. Here you also you have so many dimensions, so many parameters. This model has how many parameters? 11. So there's 10 polynomials, degree 1, degree 2, and so on, and there's actually degree 0 as well. It's the constant. So it's 11 parameters to this model over not a lot of data. So it kind of wiggles itself to go through a lot of these, right? And maybe if we had, I don't know, I'm going to try this because it's fun and I can, 50. Yeah, it just goes through every single point. No problem. So that's similar, a little bit similar to this zero error model that we had before. 30 is also very high. There we go. Okay, so on paper, this fits very well, but we get a feeling that there's something wrong here. And one way that we can see for sure that there's something wrong here is to take the process that generated the data, that function make xy, and run it again. So we fit the model to one set of data, and then we predict on another set of data or test it on another set of data. And we see that that doesn't work very well, right? So we created from the generating process, we generated another set of data. And now we can see this, for example, this stretching up here doesn't work in this case. And that's because that was kind of an outlier in some sense, right? So, well, maybe a pipeline that generates polynomials up to degree 2 is pretty good. And indeed, that looks like a pretty good fit. So, in the real world, we don't actually know what degree polynomials generated the data, but this gives us at least a recipe for how we would go about ascertaining that, right? We can do an empirical experiment that tells us, okay, here's an empirical experiment, a little widget that we built here where you can control the degree and you have like a training sample over here and a test sample over there, and you can kind of find you can change the random seed if you'd like, and the noise in the data, how many data points you have, and so on. So you could do some kind of empirical experiment to ascertain that. So here in this notebook, we saw two sides of this. One is if you have a linear regression, you stick to that, you're underfitting the data, right? The data has systematic variability in it that is nonlinear. On the other hand, if you are using a model with too many parameters, you're overfitting to the data, and we'd like to do it kind of like find the happy medium between those. And we already started showing you in this notebook how to do that, but we will elaborate more in the next notebook. Before I go to that next notebook, what questions do people have? And let me also check in here. There's no questions here. What questions do people have? Yes.
So this kind of import these things, who wrote them? Are they maintained, consistent?
Yeah, it's a good question. So for example, the scikit-learn library here is developed by, at this point, thousands of people that have contributed code of various kinds, and has, I believe there's a nonprofit that kind of maintains that, raises the funding to support the development and so on. We talk more about kind of like the software sustainability issues, but scikit-learn, for one, is a very solid, well-maintained software that has a large team of people who work full-time to maintain it. It's open source, and
They're
yeah, so there are people who are paid to do this through, for example, research grants and other kind of things. If I remember correctly, this is one of these kind of software libraries where there's a nonprofit where companies can actually become members of the nonprofit by paying, and then they could, they have the badge of honor that they've contributed, and it's used very, very widely used in many industry applications. So it's a very valuable piece of software for people out there in the real world, and that's the reason people kind of contribute to its ongoing maintenance. But it's a complicated thing. I mean, some of these things all of the things you see here are very well maintained. You'll see other software here in this workshop that's more like neuroscience software that is maintained by smaller groups. It's a more niche audience. It's a little bit trickier to keep those kinds of things. What other questions do people have? Okay, let me go on and sort of formalize it. I showed you a little experiment where we did this kind of thing where we had some data. It was generated in using some process, and then we did an experiment. We trained some all, and we tested them all separately. There's actually a formal sort of practice for how to do that, and that's called validation or cross-validation, and is the topic of this notebook. So the idea is that we can do something called model validation in order to not necessarily prevent overfitting from happening, but at least knowing when overfitting has happened. So let me show you how that works. We're going to, again, import some things, get some data. Here we have, again, the abide data with its ages. We're going to do this kind of age prediction. We're back to the age prediction problem. What we saw in the previous notebook is that one way to know that overfitting is happening is to fit the model to one set of data and then to test it on another set of data or evaluate it on another set of data. That's called cross-validation, and scikit-learn supports that by many ways, but one way is by this function called train test split. What train test split does is it takes paired set of arrays, in this case, the feature array and the label array, it takes those together, and then it creates a train test set of both the features and the labels. So once I run once I run train test split on x all y, and I give it some kind of train size, I get out of that, here, I'll just verify all the shapes, x test. And this is not there's nothing magical here. It split the x into half and half. Here we have a training set that has 502 samples, and here we have a testing set that has 502 samples. Here we have labels for 502 subjects, and train labels and test labels. And importantly, these 500 are the same as these 500. That's the most important part here. That's all the magic here. Is it takes the same 500 rows from X and from Y and matches them, so each row matches. So we don't keep track. So we don't lose track of which subject belongs to which subject's features belong to which subject's. That's all this function does. Very useful because we can then do the following exercise. We can go back to our linear regression estimator. We can fit it with X train and Y train. And then we can score it. In this case, we're going to score it two different ways. We're going to score it with the training data. We're going to score it with the test data. And we're going to get a coefficient of determination for both the training data and the test data. And so this repeats the experiment that we did a couple of notebooks ago, right? We had 1,440 features, and we fit them all, and then we scored it, and we got an R-squared of 1. Now when we do this on the test sample, we get an R-squared of negative 0.64. Who here is surprised that this number is negative, just out of curiosity? Okay, not a ton of you, but a couple of you. Maybe someone who isn't surprised can explain why this number is negative. How can a variance explained be, how can an R squared be negative? How can a squared number be negative? Someone know how this works? Okay. The coefficient of determination, this depends a little bit on the math behind the coefficient of determination. The coefficient of determination is the magnitude of the error of the model relative to the magnitude of the variance in the original data. So how large are the errors relative to the variance in the labels? And the error can be arbitrarily large. So if the error is larger than some number, then it'll be negative, it'll go negative. And that number actually, there's kind of a reasonable logic here. That number is actually the error that you would get if you guessed the average age for everyone. So there's a baseline model here that you can think about. That baseline model is a very simple model. It's for every individual, predict the average of the sample. And if you predict the average of the sample, you get an R squared of 0. But you can imagine models that are worse than that, right? You can imagine a model that for every individual predicts an age of 1,500. And that model is going to be worse than this baseline mean model. So models that are worse than this mean baseline model, they get negative coefficient of determination. That's what happened here, in fact. And this is again, it's similar to these wiggles, like fitting to every wiggle. It's once you look at a different data set, and this is done on this is done on the test set, it's just off, completely off. It just doesn't work at all. It overfit to the characteristics of the original data. And by overfit, I mean there might be some signal in these brain features about differences in age, but there's also other things in there, and those other things overwhelm the signal because of age, and so it's kind of like so flexible that it reaches, like that wiggly polynomial, it reaches to various points in this space that make no sense, and there the errors are just very, very big. So that's why we got this. We didn't get this in the training sample because the training sample is fit very accurately. The model captures all of the variance in the training sample, but in the test sample, not so great. So okay, maybe less is more here. So you could do all kinds of experiments. For example, you could say, well, we took 1,440 samples. Maybe that's too much. Let's take 200 samples instead and train that. And turns out that's actually not too bad, right? It's a little bit, where were we? It's kind of 200 samples is like somewhere here on the curve. So it's not perfectly fit. Instead, it's, in the training sample, it's like 0.8. And in the test sample, it captures something like 50% of variance, which not so bad, actually, right? 50% variance of the age is not so bad. And this is in subjects, again, are subjects that were held out in the training phase, completely held out data. So it's kind of neat. There are systematic ways of doing this kind of experiment. One systematic way is called k-fold cross-validation. I won't go into too much detail about this here. We show a schematic of this. The idea is that you repeat this kind of experiment k times, and each time through this experiment, you remove a proportion of the data as a test fold. It's like, let's say you do this 10 times, you remove 1/10 of the data, you fit them all to the remaining 9/10, and you test on this, and then you repeat that 10 times, such that every observation in the data set has been in the test for one of these 10 times, right? So now you can estimate an error for every single individual in the data set for a model that was fit in the absence of that sample in the training set, right? It's always, all the errors are estimated on test data, but they're estimated for everyone because you did this kind of k-fold experiment. And there's some code here that does this very, very explicitly, kind of shows you how the mechanics under the hood are, but I'm going to skip that and just show you that you can use scikit-learn's cross-val score, which does the full experiment. You tell it how many folds you want, you tell it what estimator you want to use, and then it takes, in this case, X small, I think is the 200 features, it does the full experiment, in this case, 5 times, and it gives you scores for every individual fold. So in this case, the error was estimated 5 times, and you get, mean cross-validated R score of 0.6 in this case. So this is also neat because it's concise. You can look over this code that kept track of indices and all these things in order to do k-fold the explicit way. It's much nicer to have code that somebody else wrote that has been tested thoroughly that does this for you. Okay, this is cool. So 0.6. What's wrong with this picture, do you think? What went wrong in this experiment? Why is 0.6 not a great answer to the question, how much variance is explained by brain features? How much variance in age is explained by brain features? Does someone have a guess for what's going wrong here?
Maybe you have to calculate the squared R for the test data.
This is calculated on test data. Here we've done the experiment, and it's every time it's separating out a test. So this does cross-validation, separating train from test. So that is not the problem here. There's another more kind of tricky, subtle problem that is happening here. Why is it the case that 0.6 is overly optimistic for an estimate of brain age here? It's a hard one. It's tricky. It was hidden in something that I told you a long, long time ago. And that's the fact that this data comes from multiple different sites. And the distribution of ages in the different sites is not uniform. So if you can guess from the data which site an observation came from, you have a lot better chance of guessing the age of that individual. And in fact, when you residualize, that is, you for every individual, you replace their age with age relative to their site, the situation is not great at all. So there's not actually a lot of signal here about brain age. There's a lot of signal apparently about sight in this data. And that's just a neuroimaging thing that you might be aware of. But along the way, I mentioned sight a long time ago, and that probably flew by you as I told you a lot of other complicated things. But I think there's a lesson here also for like what to think about when you're doing machine learning. These algorithms are great. They're very, very powerful, but they will discover signal whatever way they can. And often you won't know what is the signal that they are discovering. So in this case, it's a signal probably about sight, not about it. Okay, setting that aside, but good lesson. So, okay, the question is, should we give up here? And the answer is maybe not. This is hard, and we can try a little bit more. But before reporting, paper, think about all the ways in which your machine learning results could be confounded by something like this. Okay. There's some other things here. There's one more big topic that I'd like to show you. So I'm going to maybe skip over, but just mention one more thing, that is that there's another kind of approach to cross-validation, which is, let's say you're doing an experiment, you're saying, well, I'd like to know that number 200 that you gave me, right? You chose 200. Let's say that we ignore this whole site thing for a second, and we say, oh yeah, okay, 200 seems like a good number. Where did you come up with that number? I mean, I could have tried every number between 1 and 1440 and just selected the one that came out the best. And that's also a bit of a problem. You start getting into the situation where you have this kind of hyperparameter that you're adjusting to the data. So something that you might want to do when you do these kinds of things is to do what's called nested cross-validation. That is to set your hyperparameters in inner loop. So you split the data into train and test. It's a little bit like the exploration data set versus validation data set approaches that Katerina and Russ talked about. You leave aside some of your data in advance, And then you do all your fancy cross-validation and hyperparameter tuning in an internal process. And then when you're pretty sure that you're done with this, that's when you take out the data and you evaluate it on this test set. And that test set should not have played a role in tuning the hyperparameters, tuning the parameters, and so on. At some point, the hyperparameters, like how many features to use, they become parameters in themselves, and you're given additional degrees of freedom to kind of overfit to the data. So you have to be a little careful with that. One way to be really careful with that is to do all your work in one data set and then go and kind of freeze your model in some sense, and then go to some other data set and validate it over there. Preferably you've frozen that. Maybe you didn't have access at all to that data in advance in some way. It's in a safe somewhere that you can't touch before you're really done. Pre-registration does something of that sort for you. It kind of binds you to a particular kind of thing. You can, for example, you can do some exploration on a data set and then write your pre-registration before you approach the actual data set on which you're running. That has a similar flavor to it. All of those are good things if you don't want to fool yourself, which is a very easy thing to do. Okay. And there are other kinds of experiments you can do here. The experiment that we do here shows the relationship between number of observations and number of features and accuracy on train and test, and kind of shows you that if you have very few features, you're a lot less sensitive to the size of the sample, but your top accuracy is also not as high. So there's these trade-offs that you also need to know about, but are very hard to derive analytically, and you often need to do empirical experiments. So it's kind of tricky to know how many parameters should I put in here is a hard question to answer, because it also depends on the number of observations in a way that not only depends on those two things, but also depends on the noise on the data and other. So it's tricky. Okay, let me pause here. What questions do you have at this point? Yeah.
How do you know if it's like hyper parameter?
That's the next notebook will be, the question was, how do we know how to set these hyperparameters? That's the next topic here is exactly, yeah, we'll get exactly to that. So I'll show you something more systematic to help you think about these hyperparameters, about model complexity, kind of like a little region of machine learning where these things are actually fairly kind of elegantly defined. So that's the next notebook. But on this topic of cross-validation, and yeah.
So here we chose like 200 random features, but is it not possible that maybe some features are more important or more consistently better at predicting game?
Yeah.
Like when you're doing this for your real project, you might want to know what those are and how
Yep.
go about that process.
Next notebook will answer that one too. The question was, how do we know which features to select, right? So feature selection will be part of the next notebook as well. Yeah.
Is there a way, like when you sort of showed us that scanning sites was correlated with the variable of interest, is there a way to assess for that, or do you have to just like how would you exhaust all possibilities there?
Oh, all the possible,
Like, how
all
would
the
you
possible confounds.
Yeah.
You have to know a lot about the measurement, right? This is a workshop in neuroimaging and data science, and part of this is like you can't do one without the other. Like diving blindly into a neuroimaging data set without knowing that there are sites in there is, as you know, many of us know, is a very dangerous thing to do, and that depends on the domain knowledge. Yeah, so you have to really know the data also, I think. Yeah.
When we do validation, should we match them bracket variables of the training and test them?
Yeah, that's a really good question. So the question was, should we be matching demographic variables between train and test? And so something that we have done in the past is in classification tasks, when we set up a machine learning problem, to match the two classes on demographic variables. Now, if you think that what you're estimating is, for example, let's say age, right? Like you, in the worst case scenario here, you might be fitting your model to a certain age range and then testing on a completely non-overlapping age range. And that might be tricky because maybe the true model is nonlinear, you fit a linear model over here, it kind of completely fails. The hope is that when you do this kind of randomization, that's not going to bite you, and the model is robust enough to this kind of shifts between train and test sample ranges. And so I wouldn't necessarily for train and test sample match very precisely. But if you are doing something like classification, you want to make sure that you squeeze out. I mean, in our case, we did a classification of glaucoma, people with glaucoma and people with that don't have glaucoma. And glaucoma is highly correlated with age. So we matched for every individual with glaucoma, we matched an individual of the same age, sex, and socioeconomic status that doesn't have glaucoma, so that we can kind of separate those things. So there, I think it does matter, but I don't think for the train tests, hopefully with enough repetition, you're overcoming these kinds of shifts. Okay, let me dive into the next. So the kinds of questions that you asked here before about like, how do we know what the hyperparameters are? How do we know which features to select? That falls under a broad umbrella of what we call model selection. The idea is there's probably, if we have measurements of 1,440 features in the brain, there's probably some set of features there that are good features for us. We'd like to be able to select those features. And there's probably a good number of features to consider when we're doing this kind of selection. And that's a bit of a hyperparameter that we need to fit. And there are, so in a sense, like what is the right model entails like how many features and which are the features that get selected. And in some sense, what are the features that get selected that get marked as important in a systematic exploration? That's informative for us, like knowing that this particular part of the brain provides information about age, or that this set of areas provides information, but this set of areas provides much less information. That's something that we can actually go and interpret also later. So that's a very useful thing to do. It's just very hard when you have 1,000 measurements or 1,004 measurements and 1,440 features, because you're already in this kind of very high dimensional space. And machine learning, one of the kind of ways to think about machine learning methods are as a way to approach very high dimensional problems. So it's sort of a solution to what's called the curse of dimensionality, that once you have very large numbers of measurements, you're kind of lost in this very hard to navigate space that has all kinds of unfortunate characteristics. So here's kind of, I'll zoom into a particular corner where this is relatively easy, that's relatively easy to explain in machine learning and neat, and kind of a set of methods that I enjoy in particular to explain how model selection can work in practice. So we're going to use the same set of data as before with age prediction. I'll come back to bias and variance. No, I won't. I'll explain bias and variance now. So one way to think about the problem that we face when you have these kind of models and lots of dimensions is that, in fact, there are two sources of error in predicting the age outcome. One is variance in the outcome, and the other is bias. So imagine that you have a model, and let's go here to this bottom. Let's imagine that each one of these arrow hits in this bullseye is an estimate of the age, and this is the true age. Like each one of these should have ended up in the bullseye. And there's two ways in which these points are wrong. One is that they're not centered on the center of the bullseye, but the other is that each one of these got a different answer. Imagine that each one of these is actually, that should be the same age, right? So they're different from each other, and they're also, on the whole, kind of biased away. And those are the two sources of error. The scatter of these hits is what we could think of as variance, and the shift away from the center is what we think of as bias. And both of these cause us to be wrong in estimating the age. Now, the methods that we'll look at next are methods that do they play a trick. They incur bias. They say, let's assume, let's make some assumptions. Let's shift our average estimate away from the correct estimate, but reduce the variance of our estimates. And we'll see that there are some situations in which you can add a little bit bias and reduce the variance so much that you're actually improving your error. So that's the theoretical framework. Let's look at the practical framework. I won't go into all the, for lack of time. Let's think about what's called penalized regression. So penalized regression is a form of linear regression. We saw linear regression before, and in order to explain penalized regression, I need to explain to you a little bit what the ordinary least squares regression that I showed you before, what's the ordinary least, what are the least squares here? So what ordinary least squares does is it optimizes a particular cost function. That cost function is written down here. It's the residual sum of squares. It's the sum of the errors. So yi are all the measurements in the training data, all the labels in the training data, and beta j xij are some beta j xij are the estimates from the model. So what we're doing is we're adjusting the betas, each coefficient for each feature, such that this sum is as small as possible. We're trying to find betas such that the surface in this space goes such that for every measurement that we had originally, we get as small as possible as squared error. This is an unbiased estimate. This leads to an unbiased estimate of age. But consider a slight variation. Let's say that we moved ourselves away from this unbiased estimate. We said, I want this least squares or this minimal residual sum of squares, but I also want my betas, or the absolute value of the betas of the coefficients, to be as small as possible. So I'm adding some bias. I'm saying, I'm just going to assume that the coefficients, the sum of the absolute value of the coefficient should be as small as possible. And I'm going to penalize that by a number, lambda, that's going to be a hyperparameter that I'm going to somehow select. So I'm going to push away from the iBias solution by some amount, and I hope that I reduce variance so much that I actually improve the error. And this cost function is known as lasso regression. Its implement is an algorithm called lasso. There's also a kind of a variant of this that's actually a lot easier to understand. One nice thing about the lasso that I'll mention just is that implicitly what this does is feature selection. What we said we wanted to do. Well, let's say we have 1,440 features. This tends to push a lot of the coefficients to zero and select for you non-zero coefficients, and that gives you a relatively sparse set of coefficients that are active and lets you say this area of the brain is important and that area of the brain is important, but all of these areas here don't matter at all. Another one is ridge regression. Ridge regression is very, very similar, but instead of penalizing on the absolute value of the sum of the absolute value, it penalizes on the sum of the squared values of the coefficient. So you have slight variance on the same idea. We have a residual sum of squares plus lambda, something about the coefficients, some assumption about the coefficients. Here, okay. We're going to define a function here, plot coef path. What this will do is take an estimator, some data x, y, and alpha value. Alpha is what scikit-learn calls lambda. Sorry, there's mixed terminology here, but that additional cost that's applied to this is a hyperparameter that we call alpha in our code, and it's going to plot the coefficients as alpha changes. So you can give it a series of alphas, and it'll plot the coefficients as a function of that. Well, let's run this. It'll be much easier to explain once it's visualized. Okay, so this is lasso regression. The way to think about this is that we've changed alpha. In this case, we used alpha log spaced from 10 to the -3 to, I think, 10 to the 1 with 100 points in between. So here we are. Here, alpha, or this thing that in the equation was lambda, the cost of the absolute value of coefficients is 10. Here it's 10 to the -3. Each line here is the value of one of the coefficients. I think we're running here with 200 features, so there are 200 lines here. And what we've drawn here is how this coefficient changes as a function of this cost on the absolute value of the coefficients. First, let's go to the furthest to the right here. Furthest to the right, the cost on adding coefficients overwhelms the residual sum of squares. We don't actually care if this fits the data or not, so long as we can keep the sum of the absolute values of coefficients low. So here we've just killed all of them. Any guess what the R squared of this model is, by the way? Hmm? 0. Why? Yeah, exactly. It's kind of fitting just kind of one kind of parameter, which is the mean. So it's exactly this model would have an R squared of 0. It's kind of our baseline. Here on the left, it's doing very little to squash these. And in between, there's sort of this weird, actually interesting, it goes up, it goes down, it kind of selects features. And then the question is, okay, given these coefficient paths, which values should we choose? And this is where our previous experience with cross-validation should inform us. I'll just say, this is what ridge regression looks like, by the way. On the right, it looks very, very similar. In between, it's a lot smoother. So it's got a different kind of characteristic to it. But what we're going to do here is define a function to plot training and testing. And then we will run an experiment where we'll do a validation curve. We will fit lasso. We'll do 5-fold cross-validation. We will also fit linear regression. And we'll also compare to that. Let me run the experiment. It will be easier to explain with the visualization in front of us what exactly we did here. It takes a little while to run because doing 5-fold cross-validation on 30 points along the curve. So here again, the x-axis here is the values of this hyperparameter. How much are we squashing the parameters, or how much bias are we inducing in the shifting away from the zero bias solution? Indeed, on the furthest on the right, R squared is equal to 0. Baseline to look at is this dashed line. This dashed line is the result for the ordinary least squares linear regression. This is kind of, in cross-validation, this is the R squared for this problem with the ordinary least squares. Again, this is with 200 features, so we're not overfitting here. We're kind of fitting, it's similar to what we saw before. So this is something to compare to. And we have two curves for lasso, one for the training set and one for the test set. And those are interesting. In the training set, what happens is the further to the left you are, the less of penalty, the less you're pushing away from that center, right? So over here, the R squared is as high as it possibly can be for this problem because we're pushing it away from that center of the bullseye very little. We're inducing very little bias. As you go to the right, that value grows smaller and smaller, and that's because we are always adding some additional thing that for the for the train set is reducing or increasing the residual sum of squares in some sense. We're kind of pushing away from finding the best solution in terms of the residual sum of squares. On the other hand, in the test set, what we find is we start at some value, and then at some intermediate value of alpha, we find an optimum. And then again, it kind of crashes down here to an R squared of 0 when alpha goes too far. So this, in some sense, is a solution to the problem of model selection. You could do this kind of experiment, find the alpha that works well for you. If you did the nested cross-validation, at this point, you would fix that alpha, fit the model to all of this data, and then evaluate one last time on that held-out test set that you had. We didn't do that here, but that's an approach here, is to do this kind of fairly exhaustive experiment with a set of training data, doing nested cross-validation within that in order to find this optimum, fixing that optimum, and then applying that optimum to one final model that you would then test on a final test set. And you can do a similar experiment for ridge, and that looks similar to that. It's very squashed here. Why is it so squashed? Here it is. It's the same idea in principle, right? It's just a different set of, it's got a slightly different flavor because of what ridge is relative to what lasso is. And they each have their advantages and disadvantages. Again, you find that there's an optimum level penalizing the sum of the squares of the coefficients that results in the best cross-validated test R squared. Okay, let me pause here. What questions do you have about that? Yeah.
Then what's the criteria about choosing that penalty alpha lambda thing? Like, how do you come up with the range? It makes me worry we're manipulating to get what we want a little bit, or like, is there any standardization?
Right, so that's a really nice question. Nice question, define the question that I've written a paper about. So I'll share this paper that we wrote with Kendrick, who will be here tomorrow. We wrote a paper about that for ridge regression in particular. What alpha should you choose? How do you choose it? And there are algorithms to choose that. It's not bad if you choose a really, in the best case, you just choose the largest possible range that you can imagine.
From 0 to
I mean, in this case, this is log spaced. It goes down to 10 to the negative. It's not bad if you find an optimum. It's not typical for these things to have multiple optima in different parts of this range. So if you see an optimum, it's kind of curve that goes up and then goes down, that's pretty good. But the truth is, here we've sampled on a discrete scale, and the paper that I mentioned is a paper where we did this for ridge regression. And in ridge regression, here we're sampling a lot of different things. What we did was to find a systematic way of sampling the alpha that goes between 0 and like crush all of this, right? How to do as few as possible samples in there. Let's say you have some really big that has some nice characteristics, gives you a good chance at finding a good answer. Because theoretically there is if you sampled fine enough and you picked like a huge range, you would find a good optimum for this. So it's not but it's a real problem for the other room we're now talking about deep learning, where the hyperparameter space is ginormous. There it's a real problem. Yes.
Is interval for the test set?
Confidence intervals. Yes. So you can derive confidence intervals for many of these things using resampling approaches, like bootstrapping, where you do this experiment many times, sampling with replacement and generating distributions of these things and assessing their sizes. That's the approach we usually take.
The seed when you do the 5-cross-fold validation.
Yeah, that's an approach often taken, is to do like 100-fold cross-validation and then take the variance, right? You remember when we did cross-validate with 5, we got 5 numbers. Let's just look at the variance across those as an estimate of their, but I like bootstrap. Yeah.
Is there any sort of like multiple comparisons considerations for the number of hyperparameters that you have?
Not really. In the sense that so long as you separate train and test, there's not like it depends a little bit on your criteria, right? You have to say like, what do I consider to be like accurate, right? In many cases, like here, that's R squared of 0.6 something, that's pretty high. But let's say that your question is instead like, let me do this on 1 million voxels. And if it's non-zero, I call that a hit, right? Now you have to ask sort of like, how do I set that threshold? I've done this over millions of voxels. How do I make sure that I'm correcting for that fact? That's where I think that would play a role, but not necessarily in like, oh, I have a lot of hyperparameters. Because if you add hyperparameters, you're adding flexibility, so you're in risk of overfitting. But that flexibility, there's no way for you to leak that knowledge into if you fix the hyperparameters and test on a separate test set, there's no way that you're going to somehow gain advantage. There's no way to gain advantage by doing something over here on the train set. And then if the test set has been adequately separated, there's no way to gain advantage into it. There are many subtle ways in which leakage can happen, and there's a lot to be careful when doing things like these kinds of things with time series, for example. The past tends to affect the future, so you've got to be really careful about how you do cross-validation with time series, how you do feature selection. There's one more notebook here that we definitely will not get to today, which is all about how you use dimensionality reduction as a pre-processing step here. And that's a dangerous thing to do, because if you use your dimensionality, if you peek at the test data when you're doing your dimensionality reduction to select features, you're kind of you're peeking into the data. So that's and scikit-learn is actually designed to help you avoid leakage as much as possible, but you still need to be really careful about to think about it. Yeah. All right, and we'll get to think a lot more about this. One thing that will happen tomorrow is that we'll do these group projects, and one of the things one way to approach those group projects is to do things of this sort with the data that you'll see tomorrow as part of the group project. So the group project will kind of mix together all the things you saw today. It'll be some programming, some machine learning, maybe Git and GitHub, definitely, because your entry point will be a collaborative GitHub repository. So you'll get to get your feet wet, your hands on the keyboard to do stuff of this sort already tomorrow morning. We're at time, so I'll stop here. I'll just mention for those of you in the room that there is a campus tour led by Noah that will meet here in like 10 minutes or so to go and see the campus. And I'll see you all tomorrow morning. We'll resume at 9.